Hey guys, welcome back to my channel. Long time no see. So today let's talk about F-test. My F-test in the context of regression analysis. We talked about F-test before in the ANOVA test, right? There are different types of F-test, but today we're just focused on joint significance test, right? Joint significance test, F-test. As you can see that I changed my background because I just moved to my new permanent office, which is a bigger office than before, and have my window here and have plenty of room on my back. This bookshelf that I can move all. I'm still in the process of moving all my books to this office, and have a whiteboard, giant whiteboard, and have some bookshelf over here. And then just together, I'm sorry about the baby crying. I don't know, maybe, it's some faculty bring their babies to office today, and I just have some shiny paper to block the window on my door, and have little. I might give you an office tour some other day, but today let's focus on F-test in the context of regression analysis, joint significance test. Okay, if you want to know ANOVA test, which is also F-test, you can check out my video before. I also linked down below the comments. Okay, so without further ado, let's get into it. So suppose we have this regression, B0 plus B1 x1 plus B2 x2 plus B3 x3 plus error. So if you run this regression, if we use this regression model to explain the variation in y, right? So if we have this kind of regression equation, that means we are using, or we assume there's a linear relationship between x1 and y, x2 and y, and x3 and y, right? This is a linear regression equation. And also you are thinking x1, x2, x3 can explain some variation in y, right? You want to know why there's some variation in y. You're using x1, x3, x2, x3 as an explanatory variables. Okay, so let me draw this analysis. Let me draw this ANOVA table. So I have this sources of a variation in y, sources of variation in y, right? Y some observations, you have a big value or greater value of y, so the y1, y2, y3, right? Maybe this is 90 and this is 100 and this is 80, this is a 95. So you want to know why there's difference in the values of y. So you want to know what causes the variation in this variable, right? So sources of variation in variable y, and you're using this model, right, to explain the variation in y. So that's model, or x1, x2, x3. So one reason for the difference in y, one reason or one cause or one reason of variation in y is there might be different values in x1, different values of x2, different values of x3, right? You're using these set of explanatory variable to explain y, right? The example could be maybe y is test score, and this is study hours. So 100 study hours, 30 hours per week, 90 maybe 25 hours per week, 80 maybe 23 hours per week. So you use this variable x1 to explain variation in y, and x2 could be some other variable, gender, sex, right? This is a female, female, male, female. Maybe gender plays some role on determining the test score, and x3 could be the parents' involvement, or the parents' education level, or the family income, right? You want to know what causes variation in y. And one cause could be they have different study hours, and one reason could be female or male, right? They're different sex, and one reason could be they have different family background. So this is an explanatory variable, and the rest of variation in y is explained by this term, by residual, so error or residuals, or error, some unobserved variable. So basically you are using this model to explain variation in y, and the rest of variation in y can be explained by some unobserved variables. And now we look at how much variation in y explained by the model. So we said that in the ANOVA video, right? I have 2 ANOVA videos before. So this is sum of squares. Sum of squares give us the variation in y. Right? Explained by the model, we just use sum of squares model. And then explained by error, that's variation in y explained by error term or by the residual. And so sum of squares model, that's variation in y explained by the model. That's sum squared predicted value of y using the model minus average of y, right? Overall mean. Right? That's it. Right? So I better write it here. So sum squares, right? Sum of squared predicted value of y minus average of y. Right? And this error, sum squared error, which is predicted value of y minus observed value of y. Right? So you have the data, you can easily solve for this variation in y explained by the model and variation in y explained by the error. And then you need to find the variance, so degrees of freedom for the model, which is 1, 2, 3. Degrees of freedom for the error will be total number of observations minus number of regressors and then minus 1, right, equals n minus 4. And we learned that, right, I show you that we talked about this ANOVA table. We call this ANOVA table in the videos before, right? So that's ANOVA table in the video before. So this is an ANOVA table, and I have this sum of squares divided by degrees of freedom. Sum of squares divided by degrees of freedom, we get mean squared. So that's sum of squares model divided by degrees of freedom for the model. And this sum of squares error divided by degrees of freedom for error. Right? And then that's mean squared for the model, and that's mean squared for error. Right? And then, so this mean squared basically is sum of squares divided by degrees of freedom. So this gives us a variance. So now this term, right, this thing is the variance of y explained by the model, and this is a variance of y explained by error. Okay? Variance of y explained by the model, variance of y explained by error. By model, this is by error or residual. And then we have our F statistic. I use a different color. So F statistic. We know F statistic is the ratio of 2 variances. Right? So for F distribution, so this is a probability and this is F statistic. We know that F is a ratio of 2 sample variances, and usually normally is a positively skewed distribution, and 1 is somewhere here. The shape of this curve, of F curve, depends on degrees of freedom for the numerator and degrees of freedom for the denominator. Right? So now you have this specific value of F. So that's computed value using sample data. So you probably, this is somewhere here. This S1 squared divided by S2 squared based on sample data. So we have this computed, F computed. And so we want to compare this with 1. So we want to know whether this computed F statistic is statistically significantly greater than 1. So if this S1 squared over S2 squared is statistically significantly greater than 1, we can make the conclusion, that is, the variance of y that is explained by model divided by variance of y, which explained by error, is statistically significantly greater than 1. In other words, this numerator is statistically significantly greater than denominator. Right? That means the variance of y explained by the model is statistically significantly greater than variance in y explained by error. So that means your model is useful. The model explains a significant amount of variance of y, right, compared to error. So in order to determine if this value is statistically significantly greater than 1, we need a critical value, or we need a significance level, right? Suppose significance level alpha is 5%. If 5% is here, so this is a 5%. Okay, the area under the curve give us a probability. If this is 5% and this is F critical, okay, and this is computed, so now you fail to reject null, right? You fail to reject null, or you can make the conclusion like F computed is less than F critical, or F critical is more extreme, so you fail to reject null hypothesis, or this value, right? This value is not statistically significantly greater than 1, right? So we talk about the null hypothesis later. But if this is F, if this is a F critical, or this is a 5%, and then you can make the conclusion that this computed F is statistically significantly greater than 1. Okay, so if the numerator is statistically significantly greater than denominator, that means that means the model explains a significant amount of variance of y. That means, i.e., this model is a useful model, because your purpose is to explain the variation in y, right? Your purpose is to explain the variation in y, and by using this model, significant amount of variance of y is explained, right? Can be explained. So then this is a useful model that give us the null hypothesis and alternative hypothesis. Let me zoom out a little bit. So this F-test null hypothesis will be beta 1 equals beta 2 equals beta 3 equals 0. If all this not statistically significant, and then changing x1 associated with the 0 changing y, changing x2 associated with the 0 changing y, changing x3 associated with 0 changing y. That means none of the regressors is important determinant of y. This model is useless, right? And alternative one is this model is useful. That means at least one beta is not equal 0, right? That's model, this i.e. the model is useful. Okay, see, we just compare, we just compare more than 2 population means by comparing 2 variances. Okay, we compare more than 2, or compare population means by comparing 2 variances. So that's F-test. So F-test is also called, if this is your F-test, right? This is F-test. We call this global test or joint significance test. You test whether beta 1 equals beta 2 equals beta 3 equals 0. And alternative one is at least one beta is not equal 0. Right? At least one x, at least one of the explanatory variables is useful in explaining the variation in y. Okay? But which one? You need to do individual t-test. Right? Some of the comments ask me, some of the students ask me, what the relationship, can you compare and contrast F-test and t-test? Right? What the relationship between F-test and t-test? Why do we need F-test if we have t-test? Right? Or vice versa. So here, F-test just give you the general idea, right? Whether this model is useful, whether any of the regressors you picked is useful explanatory variable. But if you reject null, of course you want to reject null, right? If you reject the null hypothesis, that means you accept the alternative. That means your model is useful in explaining why. But which variable, which independent variable, or which explanatory variable is useful, and you should do the individual t-test. Okay, now let's stop here and hope you find this helpful. Yeah, that's it for today's video. Hope you find it helpful. Any other questions, comments, please let me know. And yeah, see you next time.